In this video, we're going to look at section 9.2, which looks at significance test about proportions. So previously, we looked at how to set up a hypothesis test and how to conclude a hypothesis test, and the p-value is given to you. In this section, we're going to look more at how to calculate that p-value. But first, let's review some of those concepts that we already looked at from section 9.1. So how does a p-value help us conclude a significance test? Recall from section 9.1 that a significance test uses data from a sample to assess a claim about a population. You can think of a test as asking a question about the parameter, and we use the statistic to help us answer the question. A significance test begins with the researcher wanting to prove a claim about a parameter. This is done by identifying two competing hypotheses. One of them must be true, either the null hypothesis denoted by HO or the alternative hypothesis denoted by HA. At the start of the significance test, we assume that the null hypothesis is true. The researcher believes the alternative hypothesis is true, and it is the researcher's job to collect data and present enough evidence to prove the alternative is true beyond reasonable doubt. Since the null hypothesis is assumed to be true, we do not look for evidence in support of the null hypothesis. And so again, notice all of the information on this page is review from that section 9.1. So when the results as extreme as the observed sample statistics are unlikely to occur by random chance alone, assuming the null hypothesis is true, we say the sample results are statistically significant. This is the same thing as saying based on the evidence provided by the statistic. If the evidence goes against the assumption of the null hypothesis and supports the alternative, then the results are statistically significant. And so remember, statistically significant meant that we had enough evidence. So if our sample is statistically significant, we have convincing evidence against the null in favor of the alternative. This is known as rejecting the null or accepting the alternative. If our sample is not statistically significant, our test is inconclusive, and this outcome is known as failing to reject the null. So our key question that we need to answer is, how unusual is it to see a sample statistic at least as extreme as that observed if the null hypothesis is true? If it is very unusual, we have statistically significant evidence against the null. The p-value helps us assess how unusual the statistic is if the null is true. And so recall the following definitions. The p-value is the chance of obtaining a sample statistic as extreme or more extreme than the observed sample statistic if the null hypothesis is true. So when the p-value is low, we will reject the null, and when the p-value is high, we fail to reject the null. So when the p-value is low, we can think of this as having evidence, and when it is high, we do not have evidence. And so that's exactly what this is saying down here. If the p-value is small, then a statistic as extreme as the observed would be unlikely if the null hypothesis were true, providing significant evidence against the null. The smaller the p-value, the stronger the evidence against the null hypothesis in favor of the alternative. So how do we know if the p-value is low or high? Well, we compare it to the significance level alpha. The significance level alpha is the threshold below which the p-value is deemed small enough to reject the null in favor of the alternative. If the p-value is less than alpha, the results are statistically significant. We reject the null hypothesis in favor of the alternative. If the p-value is not less than alpha, the results are not statistically significant and our test is inconclusive. Often, alpha is equal to 0.05 by default, unless otherwise specified. So how do we actually calculate the p-value? The p-value can be calculated as the proportion of statistics in the sampling distribution, assuming that the null is true, that are as extreme as or more extreme than the observed sample statistic. If the p-value is small, then a statistic as extreme as that observed would be unlikely if the null hypothesis were true, providing significant evidence against the null. The smaller the p-value, the stronger the evidence against the null hypothesis and in favor of the alternative. Comparing the observed statistic to the sampling distribution, assuming the null is true, requires the use of a computer. Instead of comparing the statistic to the sampling distribution, assuming the null is true, we will standardize the statistic to create what is known as a test statistic. So again, we're going to convert our usual statistic that we work with, and since right now we're working with proportions, that would be a p-hat. If we were working with means, we would have an x-bar. We're going to convert those into what is known as, what is known as a test statistic. So notice the statistic and the test statistic are two different things. and we would compare the test statistic to either a standard normal distribution or a t-distribution to find the p-value. Now you haven't learned, we did learn about t-distributions back in Chapter 8, and we've worked both in Chapter 8 and 7 with our standard normal distributions. We find the p-value by finding the area under the curve that is at least as extreme as the calculated test statistic. So which tail of the distribution we need to find the area in will depend on the inequality and the alternative hypothesis. The following image comes from this website and illustrates the different types of tests for a single population proportion. So under the alternative, if you have a left tail test, and one way to remember this is a left tail test is notice this kind of looks like an arrow pointing to the left. Your p-value will come from the left tail of your standard normal distribution. If you have what is known as a right tail test in your alternative, and again notice this kind of looks like an arrow pointing to the right, the p-value will come from the right tail. And if you have a two-tailed test or a not equal sign in the alternative, your p-value will come from both sides. And so down here on the bottom of the page, we have the definition of the three types of test. Take a moment and read over these. The further a test statistic is away from the center of the distribution, the smaller the p-value. The smaller the p-value, the greater the evidence against the null hypothesis. So let's look at an example. And I apologize, this has been split between two pages here. On your notes, it'll just be on page 12. So suppose that we have these hypotheses. Under the null, our population proportion is equal to 0.5, and we're going to look for evidence that is less than 0.5. Below are two possible observed statistics and their corresponding p-values. So we have p hat is equal to 0.45 and p hat is equal to 0.3, and here are the corresponding p-values. Which statistic provides the strongest evidence against the null and why? So let's think about this. If we had a number line, and recall that we know proportions are always between 0 and 1, and our 0.5 is in the center. So under our alternative hypothesis, what we're trying to do is we're trying to prove that the population proportion exists somewhere below 0.5. In other words, we're trying to prove that the population proportion is somewhere in this area. So we have two different potential sample proportions or statistics that we could observe. So notice we could observe a p hat equal to 0.45 or a p hat equal to 0.3. And so the question is, which one of these two statistics provides greater evidence that our population proportion really is greater than 0.5? Well, notice that p hat equals 0.3 is further away from 0.5, going in the direction of the alternative. Therefore, the p hat equal to 0.3 provides the strongest evidence. So looking at the number line, we can talk through why 0.3 provides more evidence. Let's see if we can use those p-values to help us as well. Notice the corresponding p-value for 0.45 was 0.24, and the p-value for 0.3 was 0.005. Well, remember that small p-values contain more evidence. And between the two of these, the p hat equals 0.3 has the smallest p-value. So p hat equals 0.3 provides the strongest evidence because it has the smallest p-value. So far up to this point, I've given you the p-values. Now we're going to see how to calculate them by hand. How can we find the p-value by hand? In this section, we will look at how to find a p-value by hand for a significance test involving a single proportion. How do we conduct a significance test by hand for a single proportion? So below, we have the basic steps for conducting a significance test for a single proportion. We're going to go through each of the steps generically, and then we're going to look at several examples together. The first step will be to check the assumptions. In order to use the formulas for a significance test, we first need to confirm that the sample is random and that the sample size requirements for the central limit theorem are satisfied. For a single proportion, we need to check the following sample size requirements. Notice that these look very similar to the sample size requirements when you worked with confidence intervals. The main difference is instead of p hat, we now have p naught in here. P naught is the value of the population proportion under the null hypothesis. And there's an error here. This 10 should be a 15, but this will be corrected in the notes that are on Blackboard. We're going to state the null and alternative hypothesis. We saw this earlier in section 9.1. Next, we'll calculate the appropriate test statistic. So here's the formula for the test statistic. Once we have the test statistic, we'll go through and find the p-value. And we'll do this by comparing our test statistic to a standard normal distribution. And then finally, we'll conclude the test in the context of the problem. This is also known as the interpretation. So on the next couple pages, we're going to go through several examples where we're going to work through each and every one of these steps. Pepcid is a drug that can be used to heal ulcers. Suppose the manufacturer of Pepcid claims that at least 80% of patients are healed after taking 40 milligrams of Pepcid every night for 8 weeks. In clinical trials, 139 of the 178 randomly selected patients suffering from the ulcers were healed after 8 weeks. Test the manufacturer's claim at the alpha equals 0.01 significance level. So, let's start out with our assumptions. The first thing we need is a random sample. Notice this is given to us in the problem. And we can see that right here. Next, we need to check our sample sizes. There's two things we need to check. We need to check the n times p naught, and we need to check the n times 1 minus p naught. Now n is the total number of people, and so you'll notice the total number of people is 178. And p naught is the value of the population proportion under the null hypothesis. So let's go ahead and jump down to our second step, which is identify our hypotheses. Then once we have our hypotheses identified, we can go back and finish our sample size check. Remember, for our hypotheses, we will have the null hypothesis and the alternative. Since for these examples we're working with the population proportion, we will have P. And the alternative is whatever we're trying to prove. So notice here we're trying to test the manufacturer's claim, and the manufacturer claims that at least 80% of the patients are healed. So what we're going to do is we're going to test that P is greater than 80% or 0.8. Notice we're not going to put the equal sign here, and that's because the equal sign is reserved for the null hypothesis. So now that we've identified our hypotheses, we can go and finish our sample size check. P naught is going to be whatever value is listed under the null hypothesis. So here we'll have times 0.80, and here we'll have 1 minus 0.80. Next, we'll place these in our calculator. So if you'd like to work along with me. For the first one, I get 142.4. Which is definitely larger than 15. Then for the second one, I get 35.6, which is bigger than 15. So in each cases, we've satisfied the sample size requirement. So this now brings us down to step 3. In step 3, we're going to compute our test statistic. So the very first thing I'm going to do is write down my formula. Now we've already identified P naught and N, so the last thing we need is P hat. Well, P hat is the sample proportion, very similar to when you worked with confidence intervals. So going back up to the problem statement, notice that we have 139 out of the 178 that were healed. So this tells me that P hat is equal to 139 divided by the 178. So again, we'll want to place this value in our calculator. In general, you want to take everything out to 4 decimal places. The exception to this will be when we get to the end of the calculation of the test statistic. So now that we've got our P hat, we can fill in the values of our formula. Calculating the numerator first. And then calculating the denominator. Next, taking the numerator divided by the denominator. Oh, sorry, I'm missing a 0 right here. Okay, now taking our numerator divided by the denominator. Now, when we get to the actual end step here with our test statistic, you want to calculate that to 2 decimal places. Now that we have our test statistic, we can find our p-value. So that brings us to step 4. Now, to find our p-value, what we're going to do is compare the value of our test statistic to a standard normal distribution. So to help me out, the first thing I'm going to do is just draw a standard normal distribution. Recall that standard normal distributions are centered at 0. So the next thing I'm going to do is write down where my test statistic is. Next, I need to figure out what area of the curve I'm interested in. So going back up to my alternative hypothesis, notice that this is a right tail test. We can think of this as an arrow pointing to the right. So what I'm going to do is shade in the area to the right of my test statistic. This area is the p-value. Okay. So now we need to find that area. To do this, what you'll want to do is use your standard normal curve. So if you use your standard normal table, what you should find is this area right here is equal to 0.2611. This tells me that this area, which is my p-value, is equal to 1 minus 0.2611. So if you're unsure how I found this area, go back and revisit the worksheets and the notes on when we worked with finding the area under normal curves. So our p-value in this case, we'll take the 1 minus 0.2611, and our p-value is equal to 0.7389. We're given up top that alpha is equal to 0.01. So in this case, our p-value is greater than alpha. Therefore, we will fail to reject. And then lastly, our step 5 is going to be our interpretation. And so for hypothesis test or significance test, our conclusions will look like the following. At the 1% significance level, we do not have enough evidence to conclude that more than 80% of patients are healed after taking 40 milligrams of Pepcid. So let's go back to our original problem and see if this interpretation or this conclusion makes sense. So recall that the manufacturer claims that at least 80% of patients are healed after taking the 40 milligrams of Pepcid. So we sought out to prove if that population proportion of people who were healed was really greater than 80%. And remember, we couldn't include the equal sign here for the at least because the equal sign goes here. So we're really just trying to prove if it's greater. Now, based on our sample, only 78% of people were healed. So if in the sample if in the sample only 78% of people were healed, then we should have no evidence that that population proportion is greater than 0.8. So notice that our hypothesis test did come up with the conclusion that we would expect. Let's look at another example. A team of eye surgeons has developed a new technique for risky eye operations to restore the sight of people blinded from a certain disease. Under the old method, it is known that only 30% of patients who undergo the operation recover their sight. Suppose the surgeons in various hospitals have performed a total of 225 operations using the new method, and that 88 have been successful. In other words, the patients fully recovered their sight. Do these results provide sufficient evidence that the new method is more effective than the old one? And we're going to use alpha equals 0.05 for this example. First, we're going to check our assumptions. So our first assumption we need to check is that we have a random sample. So reading through, it doesn't look like anywhere it tells us that we have a random sample of patients. So what we would say here is this is not given. And just like with confidence intervals, we're going to proceed with caution. So what we mean here is that the inference that we come up with may or may not be valid, since we don't know if this is a random sample or not. Next, we need to check our sample size. Recall the two things we need to check are n times p naught and n times 1 minus p naught, where n is our total sample size. Well, they performed a total of 225 operations, so n is 225. Next, we need p naught, but remember that p naught comes from our hypotheses, so we'll skip down and identify our hypotheses, and then come back and finish the sample size check. For our hypotheses, we list the null and the alternative, and remember for these examples we're working with the population proportion, so we use p. And notice our question here is, do the results provide sufficient evidence that the new method is more effective than the old one? Well, under the old method, it's known that only 30% of patients who undergo the operation recover their eyesight. So we would like to prove that the new method is more effective. In other words, we have more than 30% of the patients who recover their eyesight. So under the null, p will be equal to 0.30. Well, now we can finish checking our sample size requirements. And I'll place these in my calculator if you want to take a moment and do the same. Notice both of these values are bigger than or equal to 15, so we are good to go. Now that we have our assumptions and we've written down our hypotheses, we can go through and compute our test statistic. So the first thing I'm going to do is just write down my formula for the test statistic. So let me scribble that out. That wasn't very good. We've got p hat minus p naught divided by the square root of p naught times 1 minus p naught divided by n. So notice the only thing we have left that we still need to identify is our p hat. So going back up to our problem statement, it tells us that 88 of the 225 operations were successful. So again, I'm going to place this value in my calculator, and I'd like to take it out to 4 decimal places. And now that I have all the pieces, I can plug this into the formula. So first, calculating my numerator. And then calculating the denominator. And again, taking everything out to 4 decimal places. Taking the numerator and dividing it by the denominator. And remember, once you get down to the final step of the test statistic, you want to round that to 2 decimal places. All right, now that we've got our test statistic, we can find our p-value. So again, I'm going to start by drawing my standard normal curve. I'm going to draw where my test statistic falls in relation to 0. And then notice up here our arrow points to the right. We have a right-tailed test again. So I'm going to shade in the area to the right of my test statistic. So this area right here is the p-value. So again, you would want to use your standard normal curve. In doing that, you should find the area here is 0.9986. Therefore, our p-value is equal to 1 minus 0.9986, which is equal to 0.0014. So notice our p-value is less than alpha, which equals 0.05 for this example. Therefore, we're going to reject the null. Next, we can write our conclusion. I had a little bit of a glitch in the video, so you'll now see the conclusion is fully written. So take a moment, write down this conclusion, and then we'll talk through it together. So at the 5% significance level, we have enough evidence to conclude that the proportion of patients that regain their sight under the new method is greater than 0.3. So in other words, since our p-value is low, we could reject the null, and we have enough evidence to conclude the alternative. On the next page is another example. Take a moment, see if you can work through that example, mimicking the 2 that we just went through. One thing that you will want to notice is be careful when you go to find the p-value for that example. The p-value for that example will be the area in 2 of the tails. So again, pause the video, try to work that one on your own, and when we come back, we'll look at the solution. Let's look at the solution together. So notice under the assumptions, I checked the random sample assumption as well as my 2 sample size. Both of these were met. Next, I stated the hypotheses. Notice that they wanted to prove that there was evidence in change of education level among mothers. So they didn't say whether it had increased or decreased, they just said change. So since they're just looking for a change, that means it could either go up or down. So we're just looking to see if it differs from 0.31. Next, we compute the test statistic. And from here, we find the p-value. So this differs a little from the other examples, because notice when we write our test statistic below our normal curve, since this is a 2-tail, we want the area above 1.98 and the area below negative 1.98. So that's where that symmetry of the normal distribution comes into play. So using your normal curve, you should find the area to the left of negative 1.98 is 0.0239. And then we can multiply that by 2, again by the symmetry in the curve, to get the area in each of the tails. This value is 0.0478, which is less than our alpha, which is equal to 0.05, so we get to reject the null. So in conclusion, at the 5% significance level, we have enough evidence to conclude that the percentage of students reporting their mother graduated from college differs from 31%. On the next page, you have another example that you can try on your own, and you'll notice for that example, there's a separate YouTube video linked that goes through the solution. This was made for a previous class, so do note that on the sample size check there, it's going to ask for the requirement of 10, but your book for this course uses the 15. As always, if you have any questions, please let me know, but this concludes the notes for this module.